Welcome to this NPTEL lectures on robotics, basics and advanced concepts. In this week, we'll look at over-constrained mechanisms and deployable structures. So there'll be two lectures in this week. The first one will be on introduction to over-constrained mechanisms and deployable structures. I will show you some examples. And in the second lecture this week, we'll look at kinematic and static analysis of over-constrained mechanisms and deployable structures. Okay, so let's continue. So the contents of this lecture are, we'll go back and review this notion of degrees of freedom. Then we will look at over-constrained mechanisms and deployable structures. Then I will show you how we can model and analyze over-constrained mechanism. This consists of two parts. First, we will use a set of coordinates which are called natural coordinates. Then we will obtain what is called as the constrained Jacobian matrix. Okay, and then from this constrained Jacobian matrix, we will find the null space of that constrained Jacobian matrix, which will tell us the actual degrees of freedom of that mechanism, over-constrained mechanism. And it also helps us telling us which are the redundant links and joints in that mechanism. Okay, so this work was done by my ex-PhD student, BP Nagraj. He is now in ISRO as a senior scientist. Okay, so let's continue. So the degree of freedom of any mechanism is given by this Grubler-Kutzbach criteria, and it is given is very well-known formula by now, and everybody knows it by now, hopefully. So we have lambda into n minus j minus 1 plus the sum of the degrees of freedom at the j joints. So n is the total number of links, including the fixed base. J is the total number of joints, connecting only two links. So if the joint connects three links, then it must be counted as two joints. And Fi is the degree of freedom of the ith joint. And lambda is equal to 6 for spatial motion and 3 for planar motion and for planar manipulators and mechanisms. Okay, so as an example, this is a very well-known Puma 560 serial robot. It consists of one joint here, which is labeled as waist. Then there is something called a shoulder. Then there is the forearm. And then there are these three rotations at the wrist. There are three joints here. Okay, so if you substitute n equals 7, j equals 6, Fi is 1, and lambda is equal to 6, we will see that the degree of freedom is 6. This is another very well-known mechanism by now. This is a planar 4-bar mechanism. It has this fixed link, first moving link, second link, third link. Okay, so this is counted as one of the links in n. So n is 4, j is 4. There are 4 rotary joints, 1, 2, 3, and 4. And each rotary joint, the degree of freedom is 1. Okay, lambda is 3. And if you substitute back in that formula, Grubler-Kutzbach criteria, we'll get degree of freedom 1. It turns out that this Grubler criteria works for many mechanisms, but it does not work always. Especially, it does not work for what are called as over-constrained mechanisms, which we will see later. Many researchers have worked on these over-constrained mechanisms. For example, Mavrodas and Roth, Gann and Pellegrino. And there is a very nice review paper by Gogu in 2007, which gives all the reasons and how to tackle over-constrained mechanisms. So here is a set of examples, which is an over-constrained mechanism. Okay, so the first over-constrained mechanism is these 3 sliders. So basically, I have a fixed link here. Then there is one prismatic joint here and another prismatic joint here. Okay, and there is another prismatic joint here. So this R, P means basically these are the 2 different links which go into each other. R and Q. Similarly, N and M are the 2 links which form the joints. Okay, and J and K. So we have 3 sliders. If you substitute number of links and the number of joints, which is 3, the sum of degrees of freedom is 3, and lambda is 3, you will see that the degree of freedom is less than 1. However, this mechanism moves, because you can see if I pull this mechanism in this direction, this link length will increase, or this slider will change dimension. This will also move, and this will also move to adjust that you are bringing it outwards. Okay, this is another very well-known over-constraint mechanism. We have a rotary joint here, another rotary joint here, but then these two joints are prismatic joints. Okay, so it is an RPPR mechanism. And as you can see, this one has a very strange degree of freedom. This link can slide in between each other. However, if I try to rotate it, it will not move. Okay, so this is sometimes called as a passive degree of freedom, because the configuration of the mechanism really does not change, but this link which is connecting these two prismatic joints can slide. This is another very famous linkage. This is called as a parallelogram linkage. So basically what we have is a 4-bar linkage, which is 1, 8, B, and 2. But let's assume we add another link which is exactly this length, okay, at this somewhere in between, in this point here as a hinge joint, another hinge joint here. So if you now calculate again the degree of freedom according to Grubler-Kutzbach criteria, you will see that the degree of freedom is less than 1. Okay, so in this case there is a redundant link PQ. Okay, so first one, there is a special geometry. This triangle is exactly equilateral triangle, and then these lengths are chosen such that all of them are always looks like an equilateral triangle. This is another very famous mechanism which is called as a Kempes-Burmester focal mechanism. So basically, as you can see, there are many links. So there is one link, there is another link, there is another link, there are these joints. Okay, and then there is some special geometry of these quadrilaterals. Okay, and as a result, as you move this link at this joint, what you can see is that this point, okay, D, this link moves as if there were no D. Okay, so the motion of this link is about D. So even if there is no joint at this place, this link will trace an arc of a circle. Okay, so that is one of the reasons why it is called focal point, because without this joint also, if you remove this joint, then this link will trace a curve, a circular curve with the focus at D. Okay, if you apply the Grubler-Kutzbach criteria with this joint here, then you will see that the degree of freedom is less than 1. Okay, but nevertheless, this linkage moves. This is another very famous over-constraint mechanism in 3D space. This is a spatial mechanism. This is called as the Bennett's linkage. So basically, there are 4 rotary joints. Okay, these joint axes are in 3D space. They are not coming out of this screen. They are not all parallel. However, if you and there are only 4 links, 1, 2, 3, and 4. So if you were to substitute lambda is 6, the number of links is 4, and the number of joints is 4, each with 1 degree of freedom. Okay, then you will see that the degree of freedom is -2. However, it does move. And that it moves simply because there is a special geometry of these linkages. So this A1 and A3, the opposite sides are equal, A2 and A4 are equal. Okay, and these angles which these joints make, so this is beta, this is alpha, this is also alpha. And sine alpha by A is equal to sine beta by B. So where A is this A1 and A3, and B is A2 and A4. Okay, so only because of this very special geometry, very special arrangement of the joint axis, it will move. And this has been a very well-known over-constraint mechanism. Many researchers have worked on it, and then they could figure out why it moves. Okay, there are also many other over-constraint mechanisms which have degree of freedom less than 1, but they all move. So one obvious example is that of a hinge door. So suppose you have the wall and there is a hinge, okay, there is a door, but you connect this door to the wall with more than one hinge. Okay, so again, if you see that it is a, if you apply number of links and the number of joints, in this case let's say 3, then the degree of freedom will be less than 1. Okay, so this is obvious standard example of an over-constrained linkage. There is also a very famous linkage called Sarus linkage. This is a spatial 6R linkage, and it moves only because there are two groups of 3 parallel joint axes. Okay, so it does very interesting motion. Okay, some linear motion of some point, although the input is rotary. There is also a Bricard linkage. There are 3 types. These are also very well known over constraint mechanisms. These are also spatial 6R linkages. Okay, again the degree of freedom is less than 1. And they have this line plane symmetry or 2 collapsed configuration. Okay, because of this symmetry or this collapsed configurations, then that is the reason it moves. And then there is also something called Hoberman mechanism. Okay, so these are very well-known mechanisms. Again, if you go and type in Google what is a Hoberman mechanism, you will see very nice videos of mechanisms where it is radially increasing or decreasing. Okay, and it happens because the link lengths are very special. These are angulated links of special dimensions. Okay, the last set of over-constraint mechanisms are these pantograph masts. Okay, and these are used extensively in space applications. So I will look at very next slide what are called as deployable pantograph masts. So the Grubler-Kutzbach criteria fails since special geometry is not taken into account. The Grubler's formula is just based on counting. You can see it is lambda into n minus j minus 1. Okay, so n minus 1 comes from the fact that there are n minus 1 moving links. Okay, j is because j joints are adding some constraints. So that is why lambda into n minus j minus 1 is the total degrees of freedom minus the constraints which a joint j is adding. And then you sum to this number the degrees of freedom given by each joint. Okay, so it is just a simple counting argument. It has nothing to do with the geometry of the mechanism. And hence, many attempts were made to derive a more universal DOF or mobility formula. Okay, you can see this paper by Gobu. A list of such attempts are mentioned in this paper. So one well-known attempt is that we can remove the passive degrees of freedom. So for example, in the RPPR mechanism, the PP joint, the link between the two prismatic joints, it is a passive degree of freedom. It does not change really the configuration of the mechanism. Similarly, in a SS pair, if in a mechanism there are two spherical joints, one after another, then the link in between these two spherical joints can rotate freely without changing the configuration of the robot or the mechanism. So Sai suggested that we should remove all these passive degrees of freedom or passive cases. Okay. Waldron, earlier to that, he said that we need to choose this lambda properly. Okay, so as I said, lambda is equal to 6 if it is moving in 3D space. Lambda is equal to 3 if the motion is planar. So he suggested that we need to use a different value of lambda depending on what are the actual degrees of freedom. Okay, so if there are over constraint, then lambda should not be 6 or 3. The null space of the Jacobian matrix was suggested as a way to find out the actual degrees of freedom. Okay, so we find the Jacobian matrix, and this was proposed by Freudenstein, and we obtain the null space of the Jacobian, and we will use this here. Okay, of course, after 1962, many work has been done, but we are going to use a novel concept of using something called natural coordinates, which makes obtaining the null space of the Jacobian matrix much simpler. there have been also attempts to include what are called state of self-stress S and the number of internal mechanism. Internal mechanism is the end point and the base may be remaining fixed, but somewhere in between there is motion, okay, or there is no motion. So those are called, so those that were suggested to be studied and somehow taken into account when we look at over-constrained mechanisms. So let's continue. So as I said, there are these masts or large deployable structures which are used in space applications. Okay, the main reason is in space applications, the payload bay or where you will store your mechanism is very small. Okay. However, modern communication satellites and other satellites in orbit have very, very large appendages. So you could have a big solar panel because you need a very big solar panel to capture or convert solar energy to electricity. Or you can have a big antenna, but you cannot put this huge, say 5-meter antenna inside a spacecraft. So it needs to be kept folded in a very small payload bay. And once it is in orbit, it is deployed. Okay. So as I was telling you, there are many appendages which are in compact folded state in the payload bay, but becomes very large when it is deployed in space, in orbit. Most of these structures or appendages have large number of links and joints. Okay. So in stored state, it is locked, strapped, and one or less with 1 degree of freedom. During deployment, it behaves as a 1 degree of freedom mechanism because you need to deploy it and make it bigger. At the end of the deployment, the actuated joint is locked. So whether there is a motor or something else, it will become locked. And hence, even before it was a structure, because the degrees of freedom was less than 1, but once it is deployed, it becomes a structure capable of taking load. Okay, so the main ones are coilable and pantograph mass, antenna, and solar panels. These are some of the main appendages. So let me show you some pictures of deployable structures. So one of the well-known deployable structure is called FAST. It is folded articulated square mast. So each section is a square. There are these articulated joints, and you have some kind of a cable or an arrangement which you can deploy these masts. Okay, so initially, as you can see, it is kept in a very compact folded manner. Then you actuate some joints, or you actuate 1 degree of freedom, and it starts deploying. And then at the end, it will look like this long mast. So these masts are used in many spacecrafts and many space stations. So for example, 8 masts are used in the International Space Station to support solar arrays. Okay, so these are made by many companies, and one such company is this AEC Able Engineering Company. Okay, let's look at some more examples of deployable structures. So one of the common module in a deployable structure is this thing called planar scissor-like element or a pantograph. So basically what we have is we have a hinge joint here, then we have another hinge joint here, but it is on a slider, and then there are these 2 links, and in between there is another pin joint. Okay, so what happens is there is a middle revolute joint. It connects both these links which are of equal length. There is also a passive cable which connects 2 points such that it is slack when fully or partially folded and becomes taut when fully deployed. Okay, so there is an active cable, and then there are also passive cables. These dotted lines, horizontal and vertical dotted lines, and this diagonal ones are the active cables. So the passive cables terminate deployment and increase stiffness of structures. Okay, sometimes more than one passive cable is used. The active cable, basically the length of this active cable length, okay, the length of this active cable decreases continuously and control deployment. So for example, you can have a motor which is sitting here, and it will start pulling this cable. So as you can see, as it starts pulling this cable, this point will go upwards. This K and J will start coming closer to each other. Okay, and this initially it might have been collapsed, but as you start pulling this cable, this height of this structure will increase. Okay, so initially these points K and J are close to I and L. Okay, so as the active cable is shortened, J and L comes near to K and L. So these points will go this way. So this angle which is shown here, 90 degrees, will start decreasing, and then this whole structure will go up. So it will be going along the y-axis. So we can have several such SLE or scissor-like element masts, one on top of other, and then there is a cable which is running. This is an active cable along the diagonal. Okay, so what we want to do is, as you pull this cable, each of these points will start going towards each other, and the length along the y-axis will keep on increasing. So as it is shown here, the passive cables are not taut. There is an active cable which is going like this, and so on. Okay, and up to ending up here. So when you start rotating and pulling these active cables either from here or from some other place, so these points will come near to each other and the height will increase. Okay, so the deployment varies from this angle which is beta initially for some value, let's say very close to 0, and it will end up with 45 degrees. Okay, it cannot go more than 45 degrees. So in this example, there are 8 passive cables and 1 active cable. The 1 active cable goes like this. Okay, so this dark line is the active cable. We can also organize this SLE structures. SLE stands for scissor-like element, in the form of a circle. Okay, so we can have 3 different SLEs, 2 concentric circular pantograph units. Okay, and as you actuate them, as you can see, initially it is very thin and collapsed and it looks like a tube, and then as it actuates, it becomes bigger and bigger, and then finally it looks like an antenna. Okay, so this can be used to make a deployable antenna. Okay, a cable stiffened deployable antenna, because these passive cables can be made use to stiffen this whole mechanism after deployment. Okay, somewhere inside here there will be a mesh which will reflect the incoming electromagnetic radiation. Okay, so there will be a RF reflective mesh which basically gives the property or the function of an antenna. This is another one which is a well-known example. This is a 5.6 meter antenna. Okay, so as you can see, you cannot carry a 5.6 meter antenna on top of a spacecraft or on top of a rocket. Okay, so it must be kept in a nice folded arrangement. It goes up in space and then it is deployed. Okay, so this consists of circular pantograph ring and radial tension membrane rib connected to a central hub. Okay, we also need to make sure that this parabola or the surface which is generated after deployment is the right surface, okay, to act as an antenna. Otherwise it will not work. So there should be very, very smooth. The error between what you want and what is the deployed surface, okay, should be very small for the electromagnetic radiation and for the antenna to work. Okay, so this is done by all these ribs and radial tension ribs and so on. So this was a 5.6 meter by 6.4 meter elliptic version of this antenna was tested in Mir space station. Okay, so this is made by a Russian company. Okay, so now that we have seen several examples of over-constrained mechanisms and also deployable mechanisms and structures, let us see how we can analyze them. Okay, so there are various ways to model these mechanisms. And I'm going to show you 3 different kinds of coordinates which are used to model a mechanism, or which can be used to find the configuration of a mechanism. Okay, so we had looked at what are called as joint coordinates. Okay, so for example, in this mechanism, which is R, R, P, R, okay, we can say that phi 1 is the rotation of the first joint, phi 2 is the rotation of this second joint, and this translation is given by D. Okay, so we can have these 3 coordinates which specify the configuration of this R, R, P, R mechanism. Okay, so of course it is 1 degree of freedom, but then remember in the 4-bar mechanism we said there are 3 joint angles, okay, or 4 joint angles which give the configuration of this mechanism. Okay, so maybe phi 1 is enough to is the single actuated degree of freedom, but we need these two to easily say this is the configuration of this RRPR mechanism. So we have what are called as relative or joint coordinates. Basically, it's the rotation or translation at a joint relative to the previous link. Okay, so these were actually invented by Denevik and Hartenberg in '65. We can also have what are called as reference point coordinates. Okay, so the reference points coordinate consists of position and orientation of each link in the mechanism. So in this case, this is one moving link, this is a second moving link, this is a third moving link. Each of these links are moving in a plane. So if I pick a point or this link on this point, so I can say x1, y1 is the location of this point, and phi 1 is the orientation of that link. Okay, so in a plane, I can specify the position and orientation of any link by 3 coordinates, x and y coordinates, Cartesian coordinates, and some orientation angle. So these are for planar mechanisms. There are 3 such coordinates. For spatial mechanism, you need 6 coordinates. We have seen this. Any link in 3D space requires x, y, z and 3 orientation parameters. Okay. We can also have what are called as Cartesian coordinates or natural coordinates. So these are reference points moved to the joint. Okay, so instead of this point at this middle of the link, we move to the joint. So hence, in the case of Cartesian coordinates, so we have one point which is at the end of this link, which is at this joint. So it just consists of x1, y1. Then we have another point which is x2, y2 somewhere on this moving link. And there is another point which is on this link which is x3, y3. Okay, so as you can see with these 6 variables x1, y1, x2, y2, x3, y3, I can completely specify the mechanism. I can draw this mechanism if you give me all these 6 points. Likewise, using these coordinates also I can draw this mechanism. Okay, so these are the 3 ways or 3 kinds of coordinates which can be used to show the configuration of this RRP linkage. So we need to look at the loop closure equations because not all these coordinates are independent. So if you go back and substitute the number of links, joints and everything in the Grubler-Kutzbach criteria, you will see that there is this, all of these are 1 degree of freedom. It's the same mechanism. So it has degree of freedom 1. So in this case, I need 2 constraints. Why? Because I am introducing phi 1, phi 2 and D. So hence there must be 2 constraints because there is only 1 degree of freedom. In this case, I have 6 parameters. So I must have 5 constraints. In this case, I have introduced 9 parameters x, y and phi into 3 of them. So there must be 8 constraints. So we can derive these constraints. So for the relative point coordinates, it's very easy. All it is showing is that this vector plus this vector plus this vector should be equal to this vector. Okay, the standard loop closure constraint equations that we have used for 4-bar mechanism. And that can be written as some L1 cos phi 1 plus D into cos phi 1 plus phi 2 plus L3 cos phi 1 plus phi 2 minus pi by 2 is equal to L4. And likewise, the y component L1 sine phi 1, D sine phi 1 plus phi 2 plus L3 phi 1 plus phi 2 minus pi by 2 is equal to 0. So we have three coordinates, phi 1, phi 2 and D, okay, and we have two constraints and hence it has 1 degree of freedom, consistent. So if you have reference point coordinates, so we had 6 of them, okay, right? So you can see there were 6 of them, x1, so sorry, there were 9 of them. So x1, y1, phi 1, x2, y2, phi 2, x3, y3, phi 3. For Cartesian coordinates, there were 6 of them. So for this, there must be 8 constraints. Okay, and these are the 8 constraints. You can see that xa plus L1 by 2 cos phi 1 will be equal to x1. Ya plus L1 by 2 sin phi 1 is equal to y1. Okay, let's look at it just quickly. One of them. So we have x this and xa is this point here. So L1 by 2 cos phi 1 will be the coordinate of the first link. xa is the origin of the fixed coordinate system. Similarly, ya plus L1 by 2 sin phi 1 will be equal to y1. Okay, and likewise, you can show what is x2, y2, phi 2 and x3, y3. All of them are related to how they are related. Okay. So for example, phi 2 minus phi 3 is pi by 2. Okay, you can see that. So this is phi 2, which is the orientation of this link. Phi 3, which is the orientation of this link. If you see, they are 90 degrees apart. Because why? This prismatic joint, this angle is 90 degrees. Okay, so hence there are 8 constraints. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so we have these 8 constraints and the coordinates are 9 of them, and hence it is 1 degree of freedom, okay, which is what is expected. If you have Cartesian coordinates, then you have 6 of these coordinates, basically x1, y1, x2, y2, x3, y3, and xa is the origin of that fixed coordinate system, first one. So you can see that the distance is given. Okay, so x1 minus xa square plus y1 minus ya square is equal to L1 square. Okay, that's obvious, right? So x1 minus xa square plus y1 minus ya square is this L1 square. Likewise, this will be L3 square. And likewise, you will have some constraint involving d. Okay, not d, sorry, the other points. So you can show that we have one constraint which is distance, another one which is distance. This is also a distance constraint. This one involves again. So now these two constraints are slightly interesting. So what it is telling you is x2 minus x1 into x3 minus xb plus y2 minus y1 into y3 minus yb is L2 L3 cos phi. Okay, so let's look at this constraint. Okay, so we have, okay, we will come to this little later. So basically what you can show here that this x, so these three, this point, and some vector, okay, and this angle here is shown as mentioned as delta cos phi. Okay, it will be related in this form. Okay, so we have 6 variables x1, y1, x2, y2, x3, y3, and then we can write these constraints, which are 5 of them, 1, 2, 3, 4, and 5. Out of which 3 are length constraints and 3 and 2 are something to show that the vectors are in one plane. Okay, so it has also 1 degree of freedom. So what are the constraints in general when you use natural coordinates? So I have given you those equations, but where do they come from? So basic first thing is the distance between 2 points remain constant. So distance between I and j in a link or any other points in a link will remain constant. So Rij dot Rij is Lij square. If the 3 points are in along a line, okay, so then you have Rij dot Rij is Lij square, and also Rij minus k times Rij is 0. Basically, this vector from I to j is proportional to the vector from I to k. Okay. So in this example, there are 3 such constraints. The link lengths between 3 points will be constant. In this example, these 3 points are in a line. It's a special case of this. So then there is one length constraint and one which says that this vector from I to j is equal to k times this vector from I to k. So it's a fraction of that entire vector. Okay. If you have link with 3 points and an included angle, so I have a link with k, I and j, and there is an included angle alpha. So again, the distance between I and k will remain constant, between I and j will remain constant, but then the dot product of this vector I to k and I to j will be this quantity Lij, Lik cos alpha. It is nothing but the dot product formula. If you have a spherical joint, 2 adjacent links share a point. Okay, so the distance between the 2 sides of the 2 adjacent links, the distance is 0. So they share 1 point. If you have a rotary joint, okay, so I can write the rotary joint constraints in this form. Okay, so Rij dot um. So this is the link. On both sides there are 2 rotary joints. So Rij dot um is this vector along the joint axis, minus Lij cos alpha I should be equal to 0. Okay, is that true? Yes, because Rij dot will be equal to some length into cos of this angle. Similarly, Rij, this vector Rij into un dot product with this other joint axis will be equal to Lij into cos alpha j. Again, standard formula for dot product. The distance between I and j should remain constant, which is this Rij dot Rij is Lij square. Then there is a constraint which tells how these 2 joint axes are oriented. So un dot unit vectors along the joint axis is cos some gamma. Okay, so that is that gamma angle. So this is that joint axis which is translated here, and then this is the second one, and the angle between that is gamma. And finally, we have this 2 axes un and which are unit vectors. Okay, so this is the constraint due to a rotary joint. If you have a cylindric joint, which basically means that this link 2 can slide with respect to link 1 and also rotate. Okay, you can see that Rik, so I and k, this is a vector from here to here, and Rij, this is a vector from here to the other end of this link. Cross product of both of them should be 0 because they are along the same direction. Likewise, Rij from here to here, and this UC, which is the joint axis of the cylindric joint, okay, that again the cross product of that should be equal to 0. So we can derive these constraints for a rotary joint, for a spherical joint, okay, for a link, for a cylindric joint, and so on. We can also derive the constraints for a SLE pair, SLE mechanism. Okay, so SLE, remember, consists of one link, another link. It is pinned here at one place, and there are these 2 pins. So this is just scissor-like element arrangement. So if I pull these 2 together, when I goes towards L, this other hinge will go up, and then this whole thing will go up and down. Okay, so which is what was happening when you had this SLE-based masks. So in the case of an SLE, we can write the constraints in the following form. So we have one joint I, L, this distance is A, this distance is D, this distance is B, this distance is C, and we have another point K and another point J. Okay, and this is another revolute joint. So you can see Rij dot Rij, so I to J, this is single link, so the length will remain constant. Similarly, this link length will remain constant between K and L, is Lk square. Also, this point, and this point are lying on a straight line always. So Rij will be lambda 1 into Rip, and Rkl will be lambda 2 into Rkp. Okay, this is 3 collinear points. And what is lambda 1 and lambda 2? That is A plus B divided by A and C plus D divided by C. So I can simplify all these constraints in a single vector equation, which is of this form, which is B divided by A plus B into Pi. Pi is the location of this point with respect to the fixed reference coordinate system, plus A divided by A plus B into Pj minus C divided by C plus D into PL minus D divided by C plus D into Pk equal to 0. Okay, so if we think about it, this is the simplified form of all these constraints. Okay, how about boundary constraints? We will see later. We need to also impose what are called as boundary constraints. So if any point is fixed, its coordinates are 0. So the x comma y coordinate of a fixed point will be set to 0. So if you give me any mechanism, we can have this link constraint, which is also called rigid constraint. We can have these joint constraints, okay, rotary joint, spherical joint, SLE joint, whatever SLE structure, and we can have all these boundary constraints, and we can put all of them together into a set of equations. So there are NC equations, where NC is the number of constraints, which now will include all the coordinates alone, okay, x1, y1, z1, x2, y2, z2, because in the Cartesian coordinates, only the x, y, z coordinates show up. No angles will show up. Okay. So that is clear, right? So if I pick n points, then 3n is the number of Cartesian coordinates of the system, and then there will be nc constraints out of these 3n Cartesian coordinates. So what we can do is we can take the derivative of these NC equations and write in a symbolic form, which is j into delta x equal to 0. Okay, so delta x means delta x1, delta y1, delta z1, and so on. Okay, and j is the partial derivatives of these functions f of j with respect to each one of these variables x1, x2, x3, and so on. Okay, so this is a homogeneous equation. It is of the form a into x equals to 0. So this will have any non-trivial solution only if the null space of this J matrix, okay, is at least 1. Correct? So if this matrix is determinant of this matrix is not 0, then delta x will be 0. Okay. Whereas if determinant of J is 0, then we can have a non-trivial this delta capital X. Okay. So the non-trivial delta x if dimension of the null space of J is at least 1. Okay, so it turns out that the dimension of the null space of J is same as the degree of freedom of the mechanism. Okay, this is Freudenstein. So what he said was, if delta x were non-trivial, that means there is a possibility of some motion, change of coordinates, and that can only happen if the null space of J is at least of dimension 1. Okay, quickly let us take a look at the different kinds of coordinates and their comparison. So as I said, the number of Cartesian coordinates is larger than the number of relative coordinates. Why? Because the angles are, in relative coordinates you have only relative degrees of freedom. The number of reference point coordinates is the largest because reference points coordinate has x, y and phi, whereas Cartesian coordinates has only x and y, whereas relative coordinates have just some variable, either phi or d. So for the RRPR mechanism, there are 3 relative coordinates, 9 reference point coordinates, and 6 Cartesian joint coordinates are required. Okay. The number of loop closure equation is least for relative coordinates. As I showed you, there were 3 relative coordinates, 1 degree of freedom, so there were only 2. In the second case, in the Cartesian case, there were 6 Cartesian coordinates. The degree of freedom is still 1, hence there were 5 constraint equations. In reference point coordinates, we had 9 variables or 9 coordinates and there were 8 constraints. So the number of loop closure equation is least for relative coordinates. However, the loop closure constraints contain transcendental functions of the relative and reference points coordinates. You saw there were cosine and sine of phi. Okay. In the Cartesian coordinates, there are only quadratic, at most quadratic terms. There are no transcendental functions. And as a result, the Jacobian matrix, which is the partial derivatives of each of these constraints with respect to the coordinates, is at most is linear. Okay, when you derive the Jacobian matrix using Cartesian coordinates, it is linear. The number of rows in the Jacobian matrix will be more than the number of rows when you are using relative coordinates. But each row is very simple. Each element is very simple in that row. Okay, so let's go back and see how we can obtain the degree of freedom of a mechanism with constraint equations. So we add the derivative of the constraint equations one at a time in the following order. Okay, so you first add the constraint equation arising from length constraints, then arising from joint constraint. Okay, at each step evaluate the dimension of the null space of the Jacobian matrix. Okay, so either numerically or symbolically. The null space of the Jacobian, if it does not change, if it does not decrease when a constraint is added, the constraint is redundant. Okay, so think about it. So I have added 2 constraints. I add a third constraint, but the null space did not change. So hence that constraint is redundant. The boundary constraints are added last, and if the null space of the Jacobian does not decrease when you add the boundary constraint, that particular boundary constraint is redundant. Okay, so boundary constraint means where it is fixed. The final dimension of the null space is the mobility or degree of freedom of the system. Okay, this follows from the theory J into delta x equal to 0. So as long as the null space dimension of J after all the constraints have been added, whatever is left, if the nullity is 1, the degree of freedom is 1. Okay, so in summary, over-constrained mechanisms and many deployable structures do not give correct DOF using Grubler-Kutzbach criteria. Okay, and the main reason is Grubler-Kutzbach criteria is just a counting argument. It does not take into account the special geometry or the link lengths of the mechanism. Deployable structures are very important for space and other applications. Okay, and I have showed you a constraint Jacobian based approach is useful to determine the correct degree of freedom of over-constrained mechanisms and deployable structures. And I will show you that it can be used to determine the redundant links and joints which make such mechanisms gives incorrect degree of freedom from Grubler-Kutzbach criteria. So basically, as I said, when we add a constraint and if the nullity does not change, that is redundant. So you can relate it to the joint or the link from where the constraint came. Okay, so with that we'll stop. In the next lecture, I will look at kinematics and static analysis of over-constrained mechanisms.